Okay, so that was part one of the lecture on SEM. So the goals of that first part were just to use statistical models that you were familiar with, like ANOVA, correlation, simple regression, multiple regression, and show you how they can fit in an SEM framework. And that is one very, very useful aspect of structural equation modeling, is that you can use traditional statistical tools and estimate them in an SEM framework. And one of the advantages to that is SEM is really good at handling missing data in very specific ways, actually in ways that are easier than multiple imputation in a lot of ways. So the second phase is just to demonstrate for you a little bit of the flexibility of SEM, and that there are a lot of things that you can do to answer more complicated questions that you have about your research. So I'm going to show you three different kinds of models that are possible in SEM, and I'm going to start with models that include observed variables only, and that's called path analysis. So really simple approach. If you're looking at a path diagram and all you see are squares, no circles, then that's typically a path analysis. And that's a special category of SEM. Then there are models that only include latent variables. So the observed variables are then used to operationalize latent variables, and we're only looking at the relationship between latent variables. And then there also are models that use both observed and latent variables. This is also very, very, very common. So first I'll show you an example of a true what's called path analysis model. So here is an example from our friends at UCLA where we have test scores from 4 different standardized tests. So we have a reading score, a writing score, a math score, and a science score. And presumably we have measured these at different times, and we're measuring, so like time 1, time 2, time 3, and we're measuring a mediation model that shows us whether or not math functions as a mediator between reading and writing and science achievement. So does math play that role? And so this is a mediation model. It's actually a double mediation model because you have 2 variables that are flowing into one mediator. So let's see if we can unpack this a little bit. I know this looks a little complicated. First of all, which are the DVs, which are the IVs? Okay, so independent variables are exogenous, which means there are no straight paths that are going into them. That's not going to be science, right? Because we got 3 paths going into science, and it's not math because we have 2 paths going to math. But it is reading and writing. Both of these variables, we're only estimating the covariance between these two, which is 0.6 on a standardized scale. So these 2 are our IVs. These are our exogenous variables. And then we have 2 endogenous variables. We have math, and then we have science. And so simultaneously, we're estimating each one of these little paths here on this model is like a simultaneous regression. So we're estimating 1, 2, 3, 4, 5 simultaneous regressions and 1 covariance all at the same time, which is pretty cool. And what that does is it gives us estimates for all these paths so we can look at the relationships between all these things. So here's the relationship between writing and math, reading and math, math and science, so on and so forth. These E's here are the error variances. So these are the residual variances for math and for science, because endogenous variables, DVs, have to have residual variances and not regular variances. So this is an example of a path analysis. So you're taking observed variables and you're arranging them in a very specific way to measure something interesting. Here is a much more complicated version of this. In my estimation, this is pretty complicated. It might even be too complicated. But what I want to show you here is that you can use path analysis and SEM to essentially estimate something like a theoretical model, an entire theoretical model, or a flow diagram that you have created. So this is pretty cool. So this is looking at the relationships between student motivation, student self-regulation, and other social aspects of online learning. Eventually, over here, measuring satisfaction in the online course. But look at all these paths. I mean, essentially, so we have an R squared here for each one of these DVs. So we have 1, 2, 3, 4, 5 DVs, and only one IV, which is motivation. So motivation's our only exogenous variable. And we have all these complicated paths between all these different variables. So we have sort of a flow, sort of a mediated path here from motivation through perceived usefulness and sense of community. And then we have a path through social ability, and then we have a direct path to satisfaction. So this is like a super complex mediation model. But again, it's really neat because it allows you to sort of get outside the box of that sort of multiple regression setup and estimate something that is much closer to a theoretical model that you might want to test. So it can be very useful in that way. Okay, so that was type 1, which were models that involve only observed variables. Now I'm going to show you an example of a model that only uses latent variables. So this comes from a very good book that I recommend by T.Z. Keith called Beyond Multiple Regression, or maybe Multiple Regression and Beyond. I can't remember. It's a very good book. And this is his example of the relationship between all these latent variables in performance in grad school. And this is tongue-in-cheek. This isn't being serious. But here the author's taken a stab at how to represent happiness, for example. And so supposing we have measures of smiling, laughing, contentment, and satisfaction. So those are our indicators. And then those indicators are indicators of a measure of happiness at time 1 and happiness at time 2. So same indicators. And notice we learned about this last week with model modifications. We're allowing the same question or the same item measured at different times to covary with one another. That's what these arrows are down here. So the same items are being allowed to covary. Then we have some measure of social support here, which is operationalized as family and friends as a latent variable. We have some measure of aptitude, verbal, writing, and quant. And then we have performance in grad school, which is knowledge, grades, and skills. Really easy, right? I'm sure we can operationalize that very easily. No, not at all. But it's cool. It's fun to show. So basically what we're looking at, all of these pieces going around the outside, this is the measurement portion of this model. So these are the indicators. Each one of these is like a little mini CFA. So this is a CFA, this is a CFA, this is a CFA, this, and this. And that's called the measurement portion of the model. And then, once that is resolved, we also will get estimates for what's called the structural portion of the model. And those are the relationships of the paths. And that's actually where SEM gets its name. And so here, of course, we have the relationship between aptitude and performance, social support and performance. We've got some mediation going on through happiness. We've got previous happiness predicting future happiness, so some kind of a control there. And then we've got performance in grad school actually predicting happiness, which is pretty interesting too. So here, the structural portion of this model is right here. It's in the middle. All these paths here function basically as regression coefficients, and then all the measurement is going on in the outside. So that's kind of interesting. We also, more typically, will have models that include both latent and observed variables. And so this is an example from my work with Sharon Zumbren when we were interested in some measures, some EdPsych measures related to the study of writing. And so basically we were interested in writing climate, which is represented here by CP. It's kind of like how do people around you feel about writing. Oop. And then writing attitudes, which is basically like your enthusiasm for writing. So how people around you feel about writing, your own enthusiasm for writing, and how those things are related to how teachers evaluate your writing self-regulation, which is this circle here, and the grades teachers give you in writing class. So there's a lot going on in this model, but again, the same principles apply as the previous one, where we have a little CFA here for climate. So we have 3 items that are indicators of climate. We have 4 items that are indicators of writing attitudes, and we have 3 items that are indicators of teacher self-regulation. Okay, so we have observed variables here. We have latent variables for climate, attitudes, and teacher self-regulation with these indicators. And then we have an observed variable, which is grades. And that is not latent. That's a score that we actually put in for each child for the grade that they actually received. So this model then has a mix of latent variables, which are represented by circles, and observed variables, which are represented by squares. So here in the structural model, it's not all latent. I have both latent variables and I have an observed variable, and that's totally fine. A couple other things, you'll see these little circles going around the outside. These are the residual variances for each of our items and our outcomes, our endogenous variables as well. And notice here, now this is going a little bit further, notice here I've constrained the variance to 1 of this climate variable, and I'm getting estimates for each one of these paths, which is one of the things we talked about last week. So again, so now I can look at the relationship here. I've got a mediated relationship between climate and performance over here, and writing attitudes serve as a pretty powerful mediator of that relationship, which is kind of the upshot of our work in that area. Sometimes when you have a lot of indicators, it's easier to create a simplified version of an SEM model, and that's what we're doing here. So notice we have taken out the indicators. So there are 3 indicators here, 4 here, 3 here that we've removed. And so now we're just looking at the structural model, which is the relationship between our IV and our DVs. And that's totally fine to do that. Basically, this kind of approach is really cool, because what it's doing is it's simultaneously giving you information about the measurement of your latent variables. So it's removing measurement error, and it's giving you what you would typically get from a regression coefficient, which is pretty cool. So instead of scoring a variable and taking the mean of the items, we're representing them here in an SEM model, and then we're modeling it this way, which is pretty cool. So you have tools to estimate virtually any theory you might be interested in, which is pretty awesome. All right, so now we're going to talk briefly about some rules for building structural equation models. One of the things with SEM, it is super flexible, but almost to the point to a fault, right? So you can literally do anything in SEM, but that's part of the problem. You can do anything. And so some things that you can do in SEM, some models that you can build really don't make sense, either statistically or conceptually, and some can't even be estimated. And that's called a problem of identification. So the model is not identified and you won't get good solutions. But by following these rules, we can help you kind of work this out a little bit. So first of all, every path, correlation, or variance, either observed or residual, is a parameter. So we got to pay attention to this term parameter. And when you estimate a model, the number of parameters that you're trying to estimate cannot exceed the number of data points that you are putting into the model. If that's the case, if you have more parameters than data points, your model is what's called under-identified, which means it can't be estimated using SEM. using magic, using anything else. It is not a statistically valid model, and you will not be able to get estimates. Okay, so how do we get these data points? How do we know how many data points we have? It's a pretty simple formula. P times P plus 1 divided by 2, where P is the number of observed variables that you have in your model. So, for example, a very simple model with only 3 variables, 3 observed variables, 3 squares, you would have 3 times 4, which is 12, divided by 2, which is 6 total data points. So that's all you've got. You can't estimate any more than 6 parameters. And if you do, your model won't be estimable. Okay? So when we talk about model identification, a model that you come up with can fall into one of 3 categories. And 2 are okay, and 1 is really bad. So the first one is an under-identified model. This is the bad one. So that means you have more parameters to estimate than you have data points to estimate them. Another way to think about this is you have more outputs that you're asking for than you have inputs. And that just doesn't add up. You have to have at least as many inputs as you have outputs. So that's a bad thing. That's what we want to avoid. Then we have what are called just identified models. And that means you have exactly the same number of parameters as you have data points. So parameters are equal to data points. And this will work. It'll work really well. The one bummer of a just identified model is that you don't get any fit statistics. CFI, TLI, RMSEA, all those cool fit statistics we learned about last week. Your chi-square essentially will be 0 because it will have no degrees of freedom. So you're not able to get a sense of the psychometric properties of what you're measuring and how well your data fit the model, which is hard. Although we use these types of models all the time. Everything we've covered so far in the course, except for CFA, those are just identified models. So regular regression models, ANOVA models, repeated measures ANOVA, you name it, all of those models are just identified. So it's not like these are terrible models. We use them all the time. It's just if you're going to do SEM, sometimes it's nice to be able to get fit statistics too. And you get fit statistics if your model is what is called identified. And that means you have fewer parameters to estimate than you have data points, or more inputs than you have outputs. And if that's the case, then a model can be estimated and you get all those fun fit statistics that we learned about last week. Most CFA and SEM models are identified in this way. Not all, but most. So that's a real advantage, is to be able to get that information. Okay, so I'm going to show you an example of each. I'm going to show you an under-identified model, I'm going to show you a just identified model, and then I'm going to show you a fully identified or identified model. So let's start with an under-identified model. So first of all, I like to just look at this and sort of think in my head, what is it that we're trying to do here? So this appears to be a CFA model with 2 indicators, where I am trying to estimate a latent variable that we're calling negative affect. And I'm doing so looking at how changes in negative affect predict changes in anger, which I have a value for, and sadness, which I have a value for. So this is basically like a CFA with 2 indicators. So in this case, how many observed variables do we have? 2. Anger and sadness. Negative is not observed. Negative affect is not observed. It is latent. So that one doesn't count. So that means we have 2 times 3, which is 6, divided by 2. We only have 3 possible data points. So we can only estimate 3 parameters in this model. Any more than that, and we are in trouble. So let's count them up. Every circle or square gets a variance, so I'm estimating 1, 2, 3 variances, and then every path or curve, 4, 5. So there are 5 parameters that I'm actually trying to estimate, and only 3 data points. That's not good. This model actually cannot be estimated. So this is an under-identified model. The Stata will probably time out. It'll run for a while, and then it'll time out and say, I think this model's not identified. And that's what it means. It just means it's an under-identified model. Okay, so here's an example of a just identified model. Sometimes these are also called saturated models, meaning they have no degrees of freedom. Data points are exactly equal to the number of parameters that are being estimated. So one thing you'll find out, most or many of the just identified models that you'll find are actually pretty traditional statistical approaches, because those are things we use all the time. So this is a model where I have 4 observed variables: perfectionism, depression, anxiety, and SES. And I am estimating the covariance between all of these variables with each other. So if you're looking at this and if you're wondering, oh, this looks familiar, yeah, this is actually a correlation coefficient. We're actually looking at the correlations between all 4 of these variables. But let's do the math and figure out how this thing is just identified. In this case, we have 4 observed variables, which means we have 4 times 3, which is 12. No, I always do that backwards. It's p times p plus 1. So 4 times 5 is 20. Divided by 2 is 10 data points. So that means that we can estimate no more than 10 parameters. So we're estimating 1, 2, 3, 4 variances. And now I got to count up all these correlations. 1 correlation, 2 correlations, 3 correlations, 4 correlations, 5 correlations, and 6. So I've got 4 variances and 6 correlations. So that's 10. So I've got 10 data points, 10 parameters, and bingo, that is a saturated model. And really all that means, all we mean by saturated is everything is related to everything else. We've accounted for all the possible relationships between the variables in one way or the other. So this model is just identified. So this is, again, equivalent to running, this is a covariance analysis. And if we took the standardized version of this, this would be a correlation analysis, which is pretty cool. Okay, here's another just identified model. In this case, we have 2 IVs over here, perfectionism and depression, that are predicting anxiety. Anxiety is the DV, and then we're controlling for the covariance between perfectionism and depression. So in this case, I've got 3 observed variables. So 3 times 4 is 12, divided by 2 is, we've got 6 possible data points. And now let's count up how many parameters we're estimating. We're estimating 1, 2, 3 variances, 1 covariance, so that's 4, 1 path here, 5, and 1 path here, so that's 6. So we have 6 parameters. So again, this model is just identified, and it's actually equivalent to a multiple regression model. So this again would be like a regression where you have perfectionism and depression as IVs, predicting anxiety as a DV, and then you're controlling for the relationship between perfectionism and depression. All right, so we can look at a mediation model and see how this one looks. So we talked about the structure of a mediation model before. We'll go into much more detail about this one next week. But for purposes of model identification, we have 3 variables: perfectionism, conflict, and depression. So again, we have 3 times 4 is 12, divided by 2, 6 possible data points. And then let's count up how many things we're estimating. 1, 2, 3 variances. 1, 2, 3 paths. So that's 6 possible parameters. Ding, ding, ding. So this model is also just identified, and it will work. We'll get estimates from it, hopefully. Okay, so one thing to think about with SEM is particularly if you have a just identified model, like this one, for example, our mediation model. Often, if you can estimate a more parsimonious or a simpler model, it can be better because then you can obtain fit statistics, which is really, really nice. So, as I said before, just identified models are cool. We use them all the time. They're very useful. Regression, correlation, ANOVA, all these types of models are just identified. But by default, we relate everything to everything else. That's just how it works. It's safer to do that. But one thing you can think about in SEM that you can't do in regular modeling, you can look at a model like that and you can say, are there paths or covariances that you can remove that still are going to end up with a well-fitting model? And this is something you can do with path analysis in SEM. You can fit a model with fewer paths and see if the model demonstrates good fit. So here's an example. This is an identified mediation model. So in this case, we have our regular setup, A, B, C path, perfectionism, conflict, and depression. But we can actually tell the software to set that C path to 0. So in other words, we have a theory that almost all of the relationship between perfectionism and depression flows through conflict. There is very little or no direct relationship here. And if that's a theory we want to test, we can constrain this path to 0 and test the fit of a model where it only flows through conflict. And in doing so, if we assume that this path is not being estimated, then again, we still have 6 possible data points, but we're only estimating 1, 2, 3, 4, 5 parameters because this one has already been constrained. So that gives us 1 degree of freedom. And with 1 degree of freedom, you get a chi-square test, you get CFI, you get TLI, RMSEA, so on and so forth. So there are some situations where when you're thinking about a model, it can be really nice to test a simpler model that will provide you with fit statistics, especially if you think there are ways that that can be done without changing fundamentally the theory or the idea that you're trying to test to begin with. So here's another example. This is the model that I talked about before that Sharon and Zumran and I have worked on quite a bit. So this is a more complicated model. So here, let me see if I can do it without looking at my notes. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 observed variables. So 11 times 12, oh man, 11 times 11 is 121. So 132 data points divided by 2 is 66. Yes, so we have 66 possible data points. And then how many parameters are we estimating? So we're estimating 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 parameters, 14 variances, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 30 paths or covariances. 27. How did I get 27? Okay, let me go back and check. So I've got 11 observed variances. That's 3, 3. That's 3, 4, 3, 1. Yep. 15 paths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, that's right. And 1 covariance. Yep. So that's 27 total parameters. Whew. It's really taking me for a ride here. So that means we have 39 degrees of freedom because we have 66 minus 27. We have 39 degrees of freedom for this model. So that is a really identified model. We have a ton of degrees of freedom. In other words, we could add some other relationships or between variables if we wanted to, although given theory, these are the structure of the relationships that we're testing. So we probably wouldn't do that. But we do have a lot of degrees of freedom, which means that we get fit statistics and we're able to assess the kind of measurement properties of the model as well. Okay, so I think it's probably a good idea to try a little bit of practice with this, and I've put some practice on Blackboard for you if you'd like to try. So there's a handout called Model Identification Practice, and I've drawn some models for you. And it could be good additional practice to look at those and just determine, are these models under-identified, just-identified, or identified? Remember, this is the formula for data points. Determine the number of parameters and compare. And if a model is just identified, what kind of model is it? It's usually a standard statistical model, so an ANOVA, a multiple regression, so on and so forth. And then I also have a key, also on Blackboard, where you can check your work and compare and see if you got the same thing I did. And if there are any questions, we can talk about that when we meet digitally next week. So just a larger note about this, when we talk about model identification, especially when we get into more complicated models, this is a huge topic. It can be really hard, especially as models become more complex. I'll reference, as I do a lot, David Kenny's website. He's got a really nice, thorough treatment of model identification if you're interested in reading more. Some basic rules of thumb that work really well. If you want to do a CFA, which is often one of the first models that people want to try, and you're measuring a single latent construct or latent variable, you need to have at least 3 observed variables for that latent variable to be identified. Otherwise, it's going to be under-identified. If you add some constructs together or do an SEM, that can buy degrees of freedom that allow you to estimate things with fewer than 3 indicators. But as a good general rule, it's really a good idea to have at least 2 indicators to estimate a latent variable. And again, if a model is not identified, you usually can tell. The software will not give you any estimates. So again, just basically to tie in The Big Lebowski, because I love it so much. Poor Donnie in The Big Lebowski. He's the dude here, and Walter's friend. And he is frequently accused of being out of his element in The Big Lebowski. They always say, Donnie, you're out of your element. SEM is one of these areas where you can feel out of your element a little bit because there's so many possibilities. It's so wide open and flexible. And I don't mean to discourage you at all. I think it's fun to play with this a little bit. So as you keep sort of experimenting with SEM and trying some models and thinking about it, just keep those rules about model identification. Always keep in mind, what are the observed variables? What are the latent variables? What are the IVs? What are the DVs? And that's going to help you a ton. And I am always a fan of simpler SEM models. I showed you that really complicated example just to show you what's possible. But I always like to start simple and then add things on as we go. So that's it for the lecture video. There is also a demonstration of how to do this in Stata, how to estimate some SEM and path analysis models in Stata. So hopefully you find that helpful. Good luck, and I think that's all I've got. Have a good week.